last lecture we studied finite dimensional spaces and we observed the following simple properties. Suppose V is a vector space over F and W is a finite dimensional subspace of V. What we observed are the following facts. If W had a basis having D vectors, then anything above that D must be linearly dependent. Then any set in W having more than D vectors is linearly dependent. Now, using this fact, we establish that all bases for W must be finite. The moment that W is finite dimensional, it has one finite basis and consequently all bases must be finite and all bases have the same number of vectors. So, the vectors may be different in different bases, but the number of vectors must be the same in every basis. This leads to the notion of the dimension of a subspace. The dimension was just the number of vectors in a basis. So, the dimension of any finite dimensional subspace is equal to the number of vectors in a basis. The symbol means number of vectors. So, the number of vectors in a basis is called the dimension of that space. In particular, if V itself is finite dimensional, we call it finite dimensional vector space and the number of vectors in any basis will be called the dimension of that subspace. So, now suppose we have a vector space over a field F and we have a subspace W and dimension of W is D. Then we observed by the same principle as above, since the dimension is D, any D plus 1 vectors must be linearly dependent. So, any set in W having more than D vectors must be linearly dependent. And more importantly, if you have n linearly D linearly independent vectors, they must necessarily form a basis for D. So, any linearly independent set in W having D vectors must necessarily be a basis for W. So, in a D dimensional space, any D linearly independent vectors will automatically form a basis. We shall now look at some more properties of finite dimensional spaces, more properties. These were the properties which we saw last lecture. Now, we look at more properties of finite dimensional subspaces. So, again we have W contained in V and dimension of W is say D. And suppose we have a set S in W which has R vectors and is linearly independent. So, I am considering a set S in W which has R vectors and which is linearly independent. So, here is W and here is S and there are R vectors in this and they are all linearly independent, and we take dimension of W, we have taken it to be D. Now, since W is D dimensional, any D plus 1 vectors must be linearly dependent, and therefore, since S is linearly independent, it cannot have more than D vectors. So, R is less than or equal to N, since S is linearly independent and any set having greater than R is less than D, because we have taken D to be the dimension, any set having greater than D vectors in W is linearly dependent. So, R is less than or equal to D. So, therefore, the moment you have a D dimensional subspace and if you take any linearly independent set, it cannot have more than D vectors. Now, let us look at this situation. R is less than or equal to D. So, there are two possibilities. One is R equal to D and the other one is R less than D. Let us look at the case R equal to D. If R equal to D, then S is a linearly independent set, because we already assumed we have started with a linearly independent set and it has now D vectors. So, if we have a set of D vectors which are linearly independent in a D dimensional space, we have said it must be a basis. So, that says S is a basis for W. The next case is when R is less than D. If R is less than D, then obviously S cannot be a basis, because any basis for W must have D vectors, but S has only R vectors which is less than D. So, the first thing is S cannot be a basis for W since it has less than D vectors. To form a basis, we need exactly D vectors, because the dimension is D and any basis must contain D vectors. So, S cannot be a basis. Why did he fail to be a basis then? To be a basis, a set has to be linearly independent and span the space. We have already assumed it is linearly independent. So, the only way S can fail to be a basis is for not spanning W. So, S can, the only way S can fail to be a basis for W is by Ls being not equal to W. So, what does it mean? So, we have W, in that we have S which consists of U1, U2, UR, and then we look at Ls. Ls cannot be W, it has to be only a small part of W, and therefore, if Ls is not W, there is something sitting in W outside Ls. Let us say one such vector is V1. So, there exists a V1 which is in W, but which is not in Ls. So, W minus Ls. So, there exists a vector V1 which is in W, but not in Ls. But we have seen that whenever we have a subspace inside which we have a linearly independent set and we pick a vector outside that subspace, then these together must form still a linearly independent set in the bigger space. So, we take this bigger space to be W, the subspace of W to be Ls, something outside that and something linearly independent inside that, together they must be linearly independent. Hence, we have U1, U2, UR with V1 now appended is linearly independent in W. So, now we started with R vectors linearly independent in W. Since R was less than D, it was not adequate to span the whole space, and therefore, it could not become a basis. It needed help. So, we needed to supply more vectors. Now, we have supplied one more vector to the set S and made it a slightly bigger linearly independent set. Now, if R plus 1 is equal to D, then we have D linearly independent vectors in W, and the moment you have D linearly independent vectors in a D dimensional space, and hence a basis for W. If R plus 1 is still less than D, what we do is we now look at this space spanned by all these fellows together. So, if R plus 1 is less than D, then if I call this set S1, LS1 will still not span W. That means, I can pick another vector V2 outside this. So, there exists V2 belonging to W minus LS1 such that U1, U2, UR, V1, V2 is linearly independent in W. Thus, we can go on expanding this set one by one, adding vectors from outside. So, continuing this process, D minus R times we get vectors V1, V2, Vd minus R such that U1, U2, UR, V1, V2, Vd minus R is linearly independent in W. But now there are D vectors, there are R of them in the U's and the D minus R in the V's, they add up to totally D vectors, and the moment you have D linearly independent vectors, you already got a basis, and hence this forms a basis for W since there are D linearly independent vectors. So, therefore, either R is equal to D, as in case 1 we had R equal to D, in which case the starting set itself was a basis, or the case R less than D, we are able to go on supplying vectors V1, V2, Vd minus R and thereby making it a basis. So, either it is already big enough linearly independent set to form a basis, and if it is not big enough, we can supply adequate number of vectors so that it forms a basis. So, how do we conclude? So, the conclusion is that V vector space over F and we have W in V subspace dimension of W equal to D, it is a finite dimensional subspace, then any linearly independent set in W is, as in case 1, either already a basis, either a basis for W, or if it fails to be a basis, we can append vectors to it, enough number of them, so that it forms a basis. So, we get either this or it is can be extended. When we say extended, we mean we could append more vectors to it such that it is part of a basis. It is already a full basis or it is made a part of a basis. The whole thing is a basis and the u vectors are part of it. So, either the set is a basis, any linearly independent set is a basis, or it can be extended to be a part of a basis. So, that every linearly independent set can be slowly strengthened to become a basis. At least we have seen this works in the finite dimensional subspace. In particular, if V is a finite dimensional vector space, then any linearly independent set in V is either a basis for V or can be extended to be a part of a basis. Let us look at a simple example. Let us take the space, very simple space V to be F3, and let us take this subspace W. We have seen this subspace before. It consists of all the vectors in F3 of the form alpha, beta, alpha plus beta, where alpha and beta belong to F. If we take F to be R, this is what we geometrically interpreted as the z equal to x plus y plane. The third component is equal to the sum of the first two components. Consider this subspace. We have already seen that say E1 equal to 1 0 1 by taking alpha equal to 1 and beta equal to 0, and E2 by taking beta equal to 0 and beta equal to 1 and alpha equal to 0 is a basis for W. This is a basis for W because it is obviously linearly independent, and every vector in W is alpha times E1 plus beta times E2 for suitable alpha and beta. So, this is a basis for W, and how many vectors are there in this basis? There are exactly 2 vectors, and therefore, dimension of W is equal to 2. Now, suppose I take the set S, which is V1 and V2, where V1 is the vector 1 1 2 and V2 is the vector 1 minus 1 0. Let us observe first of all S is linearly independent, because you cannot get V2 as a multiple of V1, because V1 has non-zero component as third. To get V2 we can only multiply V1 by 0. So, we cannot get V2 as a linear combination of V1. Similarly, we cannot get V1 as a linear combination of V2, and therefore, V1 and V2 are linearly independent, and these are vectors in W, because V1 is obtained by taking alpha equal to 1 beta equal to 1, and V2 is obtained by taking alpha equal to 1 and beta equal to minus 1. So, S is linearly independent, it is in W, and there are exactly 2 vectors. R in this case is 2, which is equal to D, and therefore, S is a basis. Whenever you have 2 linearly independent vectors, it is automatically a basis. This is the case 1 that we discussed. Whenever you take R to be 2, it is automatically a basis. If we take now S to be only this vector 1, 1, 2, let me call it as U1, then this cannot be a basis. Here now R is 1, which is less than 2, which was D, but this is linearly independent. So, we have now started with a linearly independent set, which is smaller in size than the given dimension. So, therefore, how many vectors do we have to append in order to expand it or extend it to a basis? The total dimension is 2, we already have one vector. So, R is 1, D is 2. So, we need D minus R vectors, which is 2 minus 1. So, we need to append exactly one vector to this set to get a basis. How do we append this? We have this W, we had this S, now we are looking at LS. Our appending vector must come from outside LS. How does LS look like? The space spanned by S consists of all multiples of U1. So, LS vectors are of the form A, 2A, where A is in F, because they have to be multiples of U1. That is the only vector that is available to span LS. So, all must be just multiples of this vector U1. So, LS vectors are of this form, and we are looking for V1 outside LS. So, we want V1 belonging to W, but not in LS, W minus LS. So, it must be a vector in W, and therefore, it must be a vector of this form alpha beta alpha plus beta, but it should not be a vector in LS. Therefore, it should not be of the form A 2A, A 2A. So, therefore, V1 must be of the form alpha beta alpha plus beta for some alpha and beta, and not of the form A 2A. If it has to be of this form and not of this form, this means alpha and beta must be different, because the moment you take alpha and beta same, we get a vector of this form. So, therefore, we must choose alpha and beta such that they are different. So, we have to choose we can choose any alpha and beta, as long as they are alpha and beta are different, we will get a vector outside LS. For example, we can choose alpha equal to 1, beta equal to 2, and get V1 as 1, 2, 3. This is certainly not in LS, because for something to be in LS, the first and the second components must be equal, the third components must be double the first component. So, this and therefore, U1 V1 now is linearly independent. There are two vectors, they form a basis. This forms a basis. Now, we see that U1 is part of this basis. So, whatever linearly independent set you start with, you can make it a part of this basis. Note, our choice of V1 was not unique, because all we had to do was we had to choose an alpha and beta such that alpha is not equal to beta. We could have chosen alpha as 1, beta as 0, or alpha as 36 and beta as 27. Whatever values you choose, as long as alpha and beta are not equal, we will get a valid V1. Therefore, the choice of V1 is not unique, because we could have chosen any vector in W minus Ls as P1. For example, take alpha is equal to 1, beta equal to minus 1, you get V1 is equal to 1 minus 1 0. Then this U1 combined with this V1 is also a basis. And therefore, when we say that any linearly independent set can be extended to be a basis, the extended part is not unique. The starting part, the given set S is unique, that is what we want it to be a part of the basis, and what we append to make it a basis, that appended part can be chosen in any arbitrary manner. So, there are many ways of choosing it. Thus, the extension of a linearly independent set in W to be a basis for W is not unique. However, the fact of the matter is that we can always extend, there should be at least one extension, that is what is important for us. Now, let us look at another property of finite dimensional spaces. Suppose V is a vector space over F and V itself is finite dimensional. Say dimension of V is equal to n. So, I start with the original mother space, the basic vector space to be a finite dimensional vector space, and we take the dimension to be equal to n. Now, suppose I take a subspace of W. So, W subspace. Then any r plus 1, any n plus 1 vectors in V must be linearly dependent, because the dimension of V is n. So, any basis for W cannot have more than n vectors, because if you have more than n vectors, it will automatically become linearly dependent. So, since any set of vectors having more than n vectors is linearly dependent, any basis for W can have at most n vectors, because the basis has to be linearly dependent. If you go more than n vectors, it will become linearly a basis has to be linearly independent. If you go more than n vectors, it will become linearly dependent, and therefore, we cannot have more than n vectors and still be linearly independent. So, to form a basis, we must have at most n vectors. That means, a basis for W can have at most n vectors. That means, the dimension of W can be at most n, because the dimension is the number of vectors in a basis, and we observe that the number of vectors in a basis can be at most n, and hence dimension of W has to be less than or equal to n. If dimension of W is equal to n, then W has a basis consisting of how many vectors? Because the dimension is n, it has to have n vectors, say u1, u2, etc., un. But then the whole space is of dimension n, and we have seen that in an n dimensional space, any n linearly independent vectors will form a basis. So, these are n linearly independent vectors in V also, because they are in W and W is a part of V. Therefore, these are n linearly independent vectors in V and dimension of V is n, and therefore, any linearly independent vectors n of them will form a basis for V. So, that says u1 u2 un basis for V. Now, on the one hand it is a basis for W and therefore, it spans W, on the other hand it is a basis for V and therefore, it spans V. So, it spans W, it spans V, and since it spans the same, W must be equal to V. Hence, LW is equal to, it is not LW, let us call this set as S. Hence, S is equal to U1 U2 UN is such that LS is W, because S is basis for W, and LS is V, because S is basis for V. Comparing the two, we get W equal to V. So, therefore, what is it that we can conclude? If we take any subspace of an n dimensional space, its dimension is less than or equal to n, but if its dimension is n, it must be the whole space, otherwise its dimension should be strictly less than n. So, we conclude that any subspace of V, where V is dimension n, we are assuming that V is a vector space of dimension n, is either V or has dimension less than dimension V. So, V, let us assume the dimension of V equal to n. So, suppose we have a finite dimensional space, then any subspace of that vector space must be either all of V or must have dimension much smaller, at least one dimension smaller than V. Okay. So, whenever we want to conclude that certain subspace is exactly equal to V, one way of showing is that both of them have the same dimension. So, because we know now that if a subspace has the same dimension of the whole space, it must be exactly equal to the whole space. These are some of the simple basic properties of finite dimensional spaces, and we shall be using them very regularly without ever mentioning them again and again, because these are so genetic and fundamental properties of a finite dimensional space. Now, we are going to look at this basis. Remember, we started with the notion of basis from the idea that we are going to look at a sampling set, and then when we said that we want a sampling set, we want to do proper sampling. We do not want to do oversampling, we do not want to do undersampling. We do not want to do oversampling means we did not want redundant information, which means we do not want a linearly dependent set. We do not want to do undersampling means we wanted to span the whole space, we do not want to miss any information, which simply meant we wanted a linearly independent spanning set, and that led us to the notion of basis. Now, what is this sampling going to do and how does it help us? This is what we are going to study. Now, the role of a basis, we will see what sort of help it does in our analysis. So, first of all, let us say V is a vector space of dimension n over F. So, we have a finite dimensional vector space, its dimension is n. Okay. Now, it can have any basis, but any basis must have exactly n vectors, because the dimension is n. We now introduce the notion of an ordered basis. Well, as the word suggests, it is a basis. The only difference is when we say basis, we say a linearly independent set. So, it is a set of vectors. So, when we say a basis, we mean a set of vectors. In a set of vectors, it does not matter how we list the vectors, in what order we list the vectors. For example, if we list the vectors as u1, u2, u3, or we put u2 first, u1 next and u3 later, it does not matter. In a set, the order in which we list the vectors does not matter. However, in an ordered basis, we not only have it as a set, we insist on a particular order in which we list the sets. So, a basis for V in which the vectors are arranged in a fixed order is called an ordered basis. For example, let us look at F3, the vector space F3. Now, we know that the set of vectors E1, E2, E3 is a basis, where E1 is 1 0 0, E2 is 0 1 0, E3 is 0 0 1. We know that this is a basis for this space F3. Now, if you look at this set, this B1 as a set is the same as B. When are two sets equal? If every element of B is also in B1 and every element of B1 is also in B. Look at that way, these two sets are equal. So, B is equal to B1, these are same basis. However, if you look at the order in which they are listed, the order is totally different. Here E1 comes first, in this basis E3 comes first, in this basis E2 comes second, in this basis E1 comes second, in B basis E3 comes third and here E2 comes third. However, as ordered basis, B and B1 are different, because the vectors in the basis are ordered in a different order. So, thus we will be dealing with ordered basis. Why do we want to deal with ordered basis? Now, let us look at where this basis leads to us. V, finite dimensional vector space, dimension of V equal to n. Now, let us look at an ordered basis. How many vectors will be there in an ordered basis? Well, any basis will have n vectors. So, and in addition to that we will have an order. So, let us put B as u1, u2 etcetera un, an ordered basis for B. From now on we will write OB for ordered basis. So, the short form will be OB. So, let B u1, u2, un be an ordered basis for B. Let us take any vector x in B. Now, what do we mean by B being an ordered basis in B? First of all, it is a basis. If it were a basis, it must be linearly independent and it must span the whole space. So, in particular therefore, its span must be equal to B. So, B is an ordered basis means LB must be equal to B. Now, consider any vector x in V that says since V is equal to LB, x is in LB. If x is in LB, that means x is a linear combination of B vectors, and therefore, there must exist suitable coefficients. So, there exists x 1, x 2, x n in F such that x can be written as x 1 u 1 plus x 2 u 2 plus etcetera x n u n. So, every vector in V can be expressed as a linear combination of these basis vectors. Now, we shall see that we have used the fact that B is a basis only up to this part, namely that L B is V. We have not yet used the fact that B is linearly independent. We will use the fact that B is linearly independent to establish that for every vector this representation is unique. So, now we shall use the fact that B is linearly independent. Because it is a basis, it must be linearly independent. We shall use this fact that B is linearly independent to establish that the above representation as a linear combination of the B vectors, the above representation of any x of x in V is unique. What do we mean by that? That is, if possible, let x have another representation. What do we mean by another representation? In the representation we have this u 1, u 2, u n, but the basis is fixed, we can't change that. So, the only thing that can change are these coefficients x 1, x 2, x n. So, we have another representation means some other coefficient times u 1 plus some other coefficient times u 2 plus some other coefficient times u n. Suppose there is another such representation. On the one hand, x is x 1 u 1 plus x 2 u 2 plus x n u n. On the other hand, x is equal to x 1 prime u 1 plus x 2 prime u 2 plus x n prime u n. Now, let us subtract these two representations. Let us subtract this from this. So, what do we get? The left hand side is x minus x, which gives theta v. So, we get theta v. The right hand side we get x 1 minus x 1 prime u 1. So, we have x 1 minus x 1 prime u 1 plus etcetera x n minus x n prime u n. However, we now know that B is a basis, any basis must be linearly independent, and therefore, u 1, u 2, u n are linearly independent vectors. But then once you have linearly independent vectors, the only linear combination that will give the 0 vector is when you take all the coefficients as 0. So, that implies x 1 minus x 1 prime equal to 0, x 2 minus x 2 prime is 0 and x n minus x n prime is 0, since u 1, u 2, u n are linearly independent. So, that says x 1 equal to x 1 prime, x 2 equal to x 2 prime and so on, x n equal to x n prime. So, these two representations are the same, x 1 u 1, again x 1 prime is x 1 only. So, there cannot be any other different representation, both must be the same representation. So, therefore, what is the conclusion that we have? The conclusion is, if B equal to u 1, u 2, u n, an ordered basis for V, then every x in V has a unique representation x equal to x 1 u 1 plus x 2 u 2 plus x n u n, where the xj's are all in F as a linear combination of the basis vectors. So, every vector has a linear combination of the basis vectors, and there is one and only one way. What does that mean? It is something like, if we know the x at the sampling points, these are the sampling points of the space V, a basis is considered as a sampling set. If we know how the vector x behaves in this at the sampling point, essentially I can reconstruct the vector. So, just as we do in signals, here we get a digitization of an abstract vector. Thus, we can think of x as being made of these n scalars x1, x2, xn in F through this basis B, through this B. So, in other words, we had a vector which is an abstract quantity, it could be any type of vector space, it could be an abstract vector space over a field F, but we could always digitize it and bring it back to the scalar level. There are n scalars which are stored as the information about this vector x. The moment these n scalars and this basis, the sampling set B is known, when we can reconstruct the vector x as x1 u1 plus x2 u2 plus xn un. So, we call xi as, so we call xi as the ith coordinate, as the ith coordinate of the vector x with respect to the ordered basis, because the order is important. The moment you change the second to the third, then the second component will become the third component, the coordinate or the component. It is also called the component coordinate of x with respect to the ordered basis B. So, once we have an ordered basis for B, then every vector in V can be converted into a set of n numbers or n scalars or n elements in the field F. Elements of the field are called scalar. So, now therefore, starting from x, using B, using the ordered basis B, we now get these n scalars which I am going to write as x1, x2, xn as a column matrix, and this is obviously in Fn, and this we call, we started from x. So, x has something to do with this, we use the basis B. So, B has something to do with this. So, we denote it by xb. So, starting from a n dimensional vector space F, any vector x can be through an ordered basis converted to a vector in Fn. So, we have on the one hand we have vector space V over F, then we have this Fn, we start with a basis B for this ordered basis, then once we have this, any vector here can be converted to a vector xb in through this basis B in this space Fn. So, in other words, this is some kind of encoding of any vector in x as a vector in Fn, or you can call it digitizing a vector in V to a vector as a vector in Fn. So, we encode x in V as xb in Fn. So, however abstract the vector space V may be, as long as its dimension is n, it can always be converted to a concrete level of Fn. Fn is simply the standard n component matrix space. So, any abstract vector space, if it has dimension n, by choosing a any arbitrary ordered basis for V, every vector x can be translated, can be encoded, can be digitized as a vector x b in f n. Let us look at some simple examples. We will begin with a few simple examples. Let us look at the space V to be F 3. Always the starting example is F 3, because that is the, if you take F to be R, we get R 3, our standard 3 dimensional world where we are living. So, let us first take a basis B, which is ordered basis. So, E 1, E 2, E 3, where E 1 is 1 0 0, E 2 is 0 1 0 and E 3 is 0 0. This is our standard ordered basis. So, if we now take any vector x in F 3, it must be of the form x is equal to x 1, x 2, x 3. Now, how does this encoding take place? Through a basis. We must express this vector x as a linear combination of the b vectors. We have here b x is equal to x 1 E 1 plus x 2 E 2 plus x 3 E 3. The first component of x with respect to this basis is x 1, second component is x 2 and third component is x 3, and therefore, the encoding is just this. This is the standard encoding. Suppose I take the basis same vectors, but now I change the order. So, this is the same basis I am going to choose, but now I am going to change the order, vectors will be the same. So, I am going to take u 1, u 2, u 3, where u 1 is 0 1 0, u 2 is 0 0 1 and u 3 is 1 0 0. So, this is the E 2 of the previous case. The second vector of the previous basis has become the first vector of this basis. The third vector of the previous basis become the second vector of this basis, and the first vector of the previous basis become the third vector here. So, we have the same basis set, but we have now a different order. Now, if we take any vector x in F 3, x is of the form x 1, x 2, x 3, then x is now x 2 times u 1 plus x 3 times u 2 plus x 1 times u 3. So, what is the first component of x with respect to this ordered basis? It is x 2. The second component of this vector, now the same vector, but now we are asking for the second component with respect to this new basis, it is now x 3, and the third component is x 1, and therefore, the digitization of this vector with this ordered basis is x 2, x 3, x 1. Let us choose another basis. Let us take V 1 to be V 1, V 2, V 3, where V 1 is 1, 1, 0 and V 2 is 1, 0, minus 1 and V 3 is 0, 1, minus 1. Now, if we take any vector x which is in F 3, x is of the form x is equal to x 1, x 2, x 3, and we can verify that such a vector x will be equal to x 1 plus x 2 plus x 3 by 2 into V 1 plus x 1 minus x 2 minus x 3 by 2 into V 2 plus minus x 1 plus x 2 minus x 3 by 2 into V 3. And therefore, the new components in terms of this new basis are x 1 plus x 2 plus x 3 by 2, x 1 minus x 2 minus x 3 by 2 and minus x 1 plus x 2 plus x 3 by 2. And therefore, we get x of B 1 is x 1 plus x 2 plus x 3 by 2, x 1 minus x 2 minus x 3 by 2 minus x 1 plus x 2 minus x 3 by 2, this vector. So, the same vector will have different digitizations, different encodings in terms of different ordered basis. Of course, the natural thing therefore is look for a basis which gives the simplest digitization, where the representation becomes simple. Nevertheless, there is a fundamental question that remains. After all, if we look at the three representations that we have, it is the same vector x 1, x 2, x 3, but we have used three different bases. We have used first the E 1, E 2, E 3, then we have used this basis and then we use this B 1 basis and we get different representations. After all, they all represent the same vector x b, x b hat, x b 1, all of them represent the same vector x, and therefore, they must be somehow related. What is this relation? This will be the topic for the next lecture.